So, in the last lecture, we discussed some of the properties of continuous functions. So, we know that f is a continuous function if inverse image of every open set is open. So, that is the definition of continuous function, that f from x to y is continuous if every open set in y in its inverse image f inverse y, f inverse v is open in x. So that is definition of continuous function. And the other equivalent condition is that inverse image of every basis element is open in x. So that also we can use to prove a function is continuous. And this condition that f is continuous, it is equivalent to three conditions. First, the second first condition is that for every subset A of x, f of a closure is contained in f of a the whole closure. So this is in terms of closure of a set. Second condition is in terms of closed sets. So if inverse image of every closed set is closed, then such a function will be continuous using this theorem. And the third condition we can use is pointwise continuity. So f is continuous if and only if for each x in x, each small x in capital X, and each open set V containing fx, there is a neighborhood u of x such that f of u is contained in V. So this particular fourth condition is known as the continuity at a point x. So we discussed proof of this theorem in the last lecture. And then we were discussing some special continuous functions, how to construct certain examples of continuous function. So if I know the first example is that constant function is always continuous. So that is we checked. In the second part, we checked that the inclusion function sending every element to every element is continuous. So what is the inclusion function? Basically, it is a kind of identity function because it sends same element to same element, but its domain is a subset of codomain. So A is a subset of X here, right? So that is the inclusion function. So such a function is continuous. That is what we discussed in the last lecture. Now, third condition is that third property is that if I have a function f from x to y and g from y to z are continuous, then the composition map G circle F, which will be from x to z, is continuous. So this we already know in real analysis that if I have a two continuous function, I compose them, I will get a continuous function. Next result which we will prove is that if f from x to y, so I will write down first all statements, then I will prove one by one. If f is continuous, and if I have a subset A of x is a subspace, so it is a subspace of x, then the restriction function f restricted to A, which is a function from A to y. So from f from x to y, I construct a restriction function from a to y is continuous. Next statement is that if I have a function f from x to y, and if I take z, which is a subspace of y, this z is between the image of f, so this is range of f and y. So if I take z any set between the range of f and y, then the function which I consider from x to z obtained by restricting the range restricting the codomain is continuous, right? Because already it contains the range which is f of x. And last thing is that if instead of z is subset of y, if y is a subset of z, so if z is a space means it is not a vector space, it is a topological space having y as a subspace. So in this code, space means topological topological space. So then the function h from x to z obtained by, now what we are doing is we are considering z which contains y is a codomain. So basically we are going beyond y, and therefore this such a function is called expanding the range, the codomain of f is continuous. So this is E part, and F part. The statement of F is that the function f from x to y is continuous if x can be written as the union of open sets u alpha such that the restriction of the function f to u alpha is continuous for each alpha. So if all this restriction function f restricted to u alpha is continuous and union of u alpha is x, then f is continuous. Okay. So let us try to prove all these results one by one. So first statement is that the composition function is continuous. So we know that f is continuous and g is continuous, and we want to show that g composition f is continuous. So what we will do is we will take any open set in Z, and under this map we will take the inverse image, and we shall show that it is continuous. So if I take any open set in Z, then I know G is continuous. So if V is open set in Z, then G inverse V is open in Y, and then G inverse V is open in Y. I will get inverse image of F of that set which is open in X. So that is exactly the proof. So this is C part. So since G from Y to Z is continuous, so first of all let V be an open set in Z. So since G is continuous, G inverse V is open setting in the domain. And now since F from X to Y is continuous, so every open set in Y is its inverse image under F is continuous. So this is a particular open set in Y. So F inverse of this set is open in X. So now we are done because we know that G composition F inverse V is same as F inverse G inverse V by the set theory. And we know this set is open. So this is an open setting in X. So what did we prove is we started with open set V in Z, and for every such open set we have proved the inverse image of G composition F, inverse image of V under G composition F is open. So therefore this function is continuous. So this is a simple proof. Similarly, the D part we can prove. In D part we want to prove that F is a continuous function and A is a subset of X, A is a subspace of X, then the restriction function is continuous. So how do we define the restriction function? Basically, we are restricting the domain, right? We have the function F and we are taking only, so basically f of A is f of X, how we define restriction? Restriction of X is fx for all X belongs to A. So this is the definition of the restriction function. So if you compare this with the inclusion function, how do we define inclusion function? We are basically restriction the domain, right? We are only taking the points of the subset, the subspace. Whenever A is a subspace of X, we are defining the function by considering only elements of the set A. So if what I want to convey is that this function is a composition of the inclusion function and f. So note that f is equal f restricted to A is J composition F, where J from A to X is the inclusion function. So inclusion means whenever A is a subset of X or A is a subspace of X, I can basically consider A as a subset of X as a function using J. So that J will help us composed with F, we will get this function. And then we know that f is a continuous function that is given, and j is also continuous function. So by using C part, this function is also continuous. So now f is continuous function, and j is a continuous function. So j is continuous, we proved in the B part. So using C part, we get j composition f is continuous. Right? And what is j composition f? That is nothing but j restricted to f restricted to A. So this property is again is similar to the real analysis. All these results we already know from real analysis, but we are proving it for the general case of topological spaces. Now E part, that if I have function from x to y be a continuous function, and if I take a set z which is between fx and y, so y is codomain and fx is basically the range of f. So we want to show that the new function g from x to z obtained from f by basically restricting from y to z, this function g is continuous. So as a function, this is f from f to f from x to y, and this is a function from x to z. So how we defined that is same as gx is same as fx. Only thing change is its codomain is changed. So now we have to consider the subs. To show this function is continuous, we have to consider any open set here, and we have to show inverse image of G is open in X. So Z is a subspace of Y. So therefore, if we consider any open set in Z, so that will be of the form Z intersection open set in Y, right? So let any open set which is Z intersection U, where U is open set of Y, set in Y or set of Y. Open, basically U is a open subset of Y. So therefore, basically D is a open in Z. So what we want to prove is we want to prove G inverse of B is open set in X. So what will be G inverse B? So let us try to see this using kind of diagram. So what I have is I have function f which maps from x to y, and in y I have two sets z and u. So this is my function f. So since z contains, what we know is z contains f of x. So whatever point I take, it will land in z only, right? And G is basically f only at every point. So what is the set B? B is this set, intersection of Z with U. So what will be G inverse of B? Because fx is a subset of Z. So we can easily observe that G inverse B is nothing but F inverse U. Right, because fx is subset here, entirely contained in Z. So if I take inverse image of the function under G inverse B, then G inverse B is basically F inverse B, and F inverse B is F inverse Z intersection U, right? So what I will get is basically F inverse U. So just observe this. This is even you can take some function and try to understand this. So once we get this, then it is quite clear because f is continuous function and u is open set in y. So therefore, f inverse u is open because f is continuous. So therefore, G inverse B is open, and G inverse B is open. Therefore, G is a continuous function. So this restriction map restricting the range is continuous. That is what we proved. And what about the extension function? So second part of this each statement is regarding the extension function. So that is if Z is a space containing Y, having Y means basically Yeah, so having as a subspace. Then the function h from y to z. So earlier we are taking h from f from x to y, then I have taken y is a subset of z, and now using this function I am considering h, which is a function from x to z. So this extended function, by extending the codomain, is continuous. So that is what we want to prove. So on the other hand, h from x to z is continuous. So we want to prove h is continuous if z is having y as a subspace. And h is a it is the extension of h is defined as extension of f. So basically what here I am saying is hx is fx for all x. So now if you see that what we are doing is basically I have f from x to y, and then y is a subset of z. So this is whenever we have a subset, we basically get a inclusion function. So what is g? G is what is h? H is basically composition of so f is from x to y, and inclusion is map is from y to z. So it will be j composition f of x, right? So h is basically j composition f, and then again we know that f is continuous, inclusion is continuous, so h is continuous map. Okay, so now the last part, that is the so all these things you know why we are deriving, because this is a kind of statement that if f is continuous, g is continuous, f composition g is continuous, right? So all these things later on we can use for functions in examples. So therefore we are proving all these properties. So last part is that the function f is continuous if x can be written as union of u alpha, and each f restricted to u alpha is continuous. So let us write down the statement. So by what is hypothesis? Hypothesis is that x is a union of u alpha and so just a minute. So U alphas are open sets. So by the hypothesis X is a union of U alpha, where U alpha is open for all alpha, and what else we know is F restricted to U alpha is a continuous function. So what we shall get is we want to show F is continuous. So what we want to show is for every open set V of y, F inverse V is open. So that is what we want to show. Right. So now what is F inverse V? So F inverse V I can write as X intersection F inverse V, because X is a domain, it is a universal set, and F inverse V is always since F is a map from X to Y. So every set I can write as a intersection of the bigger set with itself. And then we know that what is X? X is the union of U alpha. Intersection F inverse V. X is union of U alpha. So we can write this, and then we can use the properties of set theory. So this I can write as union over alpha U alpha intersection F inverse V. Right. So using basically distributive law. So union is distributive over intersection, or intersection is distributive over union. Both are true. So F inverse V is basically this set, and this I can write as, so if I can show that this set is open, then F inverse V is open because it is union of such sets. So let us see what is this set. So X belongs to this set. That means what? This says that X is in U alpha such that Fx belongs to V, right? X belongs to U alpha intersection F inverse V. That means X is in U alpha as well as X is in F inverse V. X is in F inverse V means Fx belongs to V. So these statements are equivalent, or in other words, they are same statements as per set theory. And then the second condition is nothing but saying that f of, so when I apply this map on X, that belongs to V, right? Because if X is in U alpha, then F restricted to U alpha X is nothing but Fx. right? So that is this condition, fx belongs to v. So that says fx belongs to v. So combining these two, we will get these two statements are same, and this is nothing but saying that x is in inverse image of the restriction map of V. So what we have observed here is basically this set and these sets are same. So therefore we can write this set as union of f restricted to u alpha inverse image of V. And since we have already assumed that the restriction map is continuous, restriction map is continuous. So inverse image of V under this map is open. So these sets are open and then its union is F inverse V. So therefore F inverse V is open for every open set V and therefore F is continuous. So that this proves this fundamental properties about continuous functions. So we can apply this results in proving some simple results. So for example, this result which is known as the pasting lemma. What it says is that let x, which is a domain of the function which is a union b, where a and b are closed sets in x, and consider a function f from a to y and g from b to y be continuous function. So I have these two functions, f from a to y and g from b to y. These two are continuous function and union of a and b is x. So question is, can I combine this f and g function and get a function which is continuous on x? So that is this lemma. So it says that if under certain hypothesis this is true, we can extend. So what is the condition? If fx equal to gx for each element x in the intersection, then f and g combine to provide a continuous function. So this continuous function we can write as a new function h from x to y, which is defined by hx equal to fx if x is element of a and it is gx if x is element of b. So proof is simple, and after that we will see some of the examples of where we can use this theorem. So to prove this theorem, so there are many ways to prove a function which is continuous. So here you can see that the description of X is given as A union B, and A union B are closed sets. So therefore it is natural that we will use the characterization of continuous functions in terms of closed sets. So the characterization says that F is continuous if and only if inverse image of every closed set is closed. So let C be a closed set in Y. So if we can show that inverse image of this function H, inverse image of C under this function H is continuous, is closed, then H is continuous. So since we have defined Hx in terms of Fx and Gx, H inverse of C will be F inverse of C intersection G inverse of C. Alright, so this is quite simple, quite straightforward, because if you take X, which is element of H inverse C, that means Hx belongs to C. So Hx belongs to C means there are two choices for Hx, either it is Fx or it is Gx. So if Hx belongs to C, then if Hx is Fx, that will give us Fx belongs to C, and that will give us X belongs to F inverse C. And for that particular X, if Hx is Gx, then we'll get X belongs to G inverse C. So therefore this is a subset of this one, and vice versa converse is also true. So therefore these sets are equal. So Y converse is true because Fx is also Gx and Gx is also Hx for every X. So now we are done, because we know that F and G are continuous function and C is a closed set. F inverse C and G inverse C are closed sets. So what we get is, now we know union of two closed set is always closed. So F inverse C union G inverse C is closed, hence H inverse C is closed. So therefore H is continuous. So let us take some simple examples. So first function is H from R to R, defined by Hx equal to X if X is less than equal to 0, and X by 2 if X is greater than equal to 0. So what is pasting lemma? Let us go through the statement that Hx is the first function if X belongs to A and A is a closed set. Similarly, it is equal to second function over the second closed set. So here these two conditions are given. So what will be the closed sets? So x is less than or equal to 0, that means x belongs to x is less than or equal to 0. That will give us x belongs to 0 to infinity. Similarly, other way around actually. This is greater than or equal to, and less than or equal to means x is from minus infinity to 0. So this is our B because we are using here, and this is our set A. And over A, what is fx? Fx is x which is continuous on A, and gx function is the second function. First function is x. So gx is x by 2 is continuous on B. So f and g are continuous, and what we need to check is they should be same on the intersection, right? On the intersection they should be same. So intersection means intersection of these two sets. So that is singleton 0. So on 0 this function is 0, this function is also 0 at x equal to 0. So therefore that condition is satisfied, right? This condition is satisfied, fx equal to gx on the intersection. So only thing we need to check now is f and g are continuous on A and B. So that is clear because fx equal to x identity function is always continuous on this closed interval. Same way this function is always continuous on this interval, right? So therefore f and g satisfy the hypothesis of the pasting lemma, therefore h is continuous. Right, so let me give you some exercises which I could not cover in today's lecture. So just consider this function k from R to R defined by kx equal to x minus 2 to x plus 2 for x is less than or equal to 0 and for x is greater than or equal to 0. So is k continuous? So just check using whether using pasting lemma we can say this or not. And the next function is L from R to R defined by Lx equal to x minus 2 if x is less than 0, x is a negative number, and on the positive number we have negative. So is L continuous? So here hint is that L inverse of the open set 1 3 is 0 to 1. Okay, so This is what I wanted to discuss today.